Welcome, PCS members and friends, to our PCS IBS seminar. Today, we are happy to host Professor Xiaoquan Yu from Graduate School of China Academy of Engineering Physics and University of Otago. And our scientific host today is Sergey, who will introduce our speaker. Please, Sergey.
Yeah, okay, thank you and welcome everyone. So it's a great pleasure to have Xiaoquan Yu with us. Let me say a few things about his historical past. He did his education, essentially his Master of Science at the Capital Normal University in Beijing, China, where he finished his MS in 2008. And then he moved on to do his PhD at CISA/ICTP in Trieste, Italy, with at that time advisor Markus Müller, and he finished his PhD in 2012. And then he moved on to a postdoc position, worked together with me and others at the New Zealand Institute for Advanced Study in Auckland, New Zealand, where he worked for 2 years, and that's where we met for the first time and had some nice collaboration together. And then this was not far and south enough for him, so he decided to move even further because New Zealand, has two islands, the Northern Island, and then an even further island south, which is almost at the Antarctic. And he moved there to the University of Otago, where he spent quite some time working with Blair Blakey and others, and I guess we will see results of this work also today here. And then he received an offer and accepted the offer to become an assistant professor at the Graduate School of China Academy of Engineering in Beijing in 2019. But as far as I know, he spent quite some time still then back in Otago because of the worldwide pandemics. But then at some point he moved. So now he did move for some years already. He's now in Beijing, working there with having PhD students and continuing his work on ferrodark solitons and snake instabilities, or the absence of snake instabilities. So let's welcome our speaker.
It's really my great pleasure to visit PCS and give a seminar talk. And also, thanks a lot for the introduction. And today I want to share some recent progress on this ferrodark solitons. And so I guess 2 years ago, I gave an online talk on this subject. And there will be some overlap between this talk and the previous talk. And I try to present from a different perspective, but it will be unavoidable overlap. However, today I probably want to emphasize this so-called snake instability. Before we talk this paradox, let's give a general motivation why we want to discuss topological excitation in superfluids. As we all know that those topological excitations, nonlinear excitation somehow shows quite big the property or deeper property of the superfluids, and those dynamics of the this topological defect already very interesting, like vortices and solitons. More than that, those topological defects play a very important role in many important or interesting processes. Particular quantum vortices. It is well known that the 2D superfluid transition is a greatly costly solid transition that's driven by vortex anti-vortex pairs, breaks, and recombining. So that's really gives a new perspective of 2D transitions with continuous symmetry. And also, of course, vortices play a very important role in this phase ordering or Capel-Zulik, and also quantum turbulence. However, the dark soliton, or in general, that topological defects related to associated with the state 2 symmetry play a less important role in those processes. The reason is that, like dark soliton, it's very easy to couple to linear modes, even in 1D. So if there is a perturbation or a little bit finite temperature, those dark soliton basically decays very fast, so it never become essential, becomes very important or very relevant to determine some universality class of those out of equilibrium process or even finite temperature phase transitions. And moreover, in a high dimension, this dark soliton suffer this so-called snake instability. So basically, in a high dimension, before doing anything interesting, the dark soliton decays. So
what is the meaning of the dark?
Dark. Okay, I will come to this in detail. Dark means that the density at the core of the excitation is 0. So that means dark because the background has finite density. However, this inside the core of the excitation, there's no density, density 0. That's why I call it dark compared to the background density. So,
sorry, what are the examples of linear mode?
Like the Bogoliubov modes, that's the linear excitation of the superfluid.
For example,
For example, phonon. Yes. And also, of course, it's not only phonon, but for example, if there's finite temperature, there's also uncondensated atoms. It's very easy to destroy this with excitation. So that's why this G2 symmetry related excitations pay less attention to people because they are quite fragile. Now, so things may change with this finding of ferrodark solitons. So this is also a Z2 topological excitation. However, in magnetization, not in density or in wave function. And this soliton is realized in spin 1 of Bose-Einstein condensate, and this citation exhibits Euro properties, and those Euro property may help or drive or make the solitons relevant in those processes. What I just mentioned, for example, transitions, finite temperature transitions, and out of equilibrium process. So at least I think after the talk, we can say that there is a hope to see those excitations may become quite relevant in those processes. Okay, before I go to this spin 1 system, let me just give a very general review of the scale, the dark solitons in scalar BECs. The reason why I want to do this is because the soliton, the property of this soliton exhibit, it's quite general. It's a very general property for various of topological solitons, and then that's why I want to give a very brief introduction of it. And so what I'm writing here is a so-called Gross-Pidievsky equation, which governs the dynamics of the condensate at a very low temperature. And here, G is a coupling constant. Here we consider a positive coupling constant. It is certainly related to proportional to the scattering length of the atom in autocalled gas. And this equation allows exact solution like this. This is a soliton solution. And here, V is the propagating velocity of the soliton, and C the speed of sound. And at V 0 for the stationary soliton, and the wave function looks like this. This is probably quite familiar to people. This is a kink solution. A kink means that it is a excitation that interprets two ground states. Because the ground, for example, the wave function changes sign when cross the core. So that's really kind of interpreted two ground states. That's why I call it kink. And this is topological. In sense, one can calculate, say, the topological charge, or there's in terms of phase, there is a pi phase jam. this is for zero velocity. However, for the large velocity, say the velocity is approach to a speed of sound, one can see this part becomes very small, and therefore this soliton basically connected to the low-lying linear excitations. So it is a non-linear excitation. However, when the velocity is big or approach to speed of sound, it connects to the low-lying excitations. That somehow explains why those excitations are very fragile when they start to propagate. And so another property is the so-called snake instability. Let's consider a line soliton in a free space, and we can think a transverse deformation of this line. And this excitation is unstable. It means that those deformation the deformation amplitude will grow with time, exponentially grow with time, and eventually will break the soliton.
So wait, this is not a 2D, right?
This is in 2D.
And before you talked about 1D.
Before I'm writing here is only 1D, but now we extend this solution to still a 1D line, but in two-dimensional space. And then we have a new.
So basically, your field is not depending on y, but only
yes.
depending on x.
Yes,
Yeah?
yes. Once it's straight, it's only depend on x. But when we introduce perturbation, it certainly depend on y.
But let me ask you something.
Yeah.
So in case of 1D, is your solution stable or it develops instability in time as well?
In one dimension, it is stable.
Okay.
Because I'm just showing this this picture. So this picture from this scenario paper, it's published a long time ago. Here, they calculate the excitation energy of this transverse excitation, and this excitation energy had the imaginary part. And this imaginary part, this plot is the imaginary part of the excitation energy as a function of the k. K means it's the wavelength of this transverse excitation. So therefore, one can say that when k is 0, so let's go to 1D and the imaginary part vanishes. So there's no snake instability in 1D.
Well, you cannot even define a snake in 1D.
Exactly, because in 1D, there's no transverse direction.
Well, what you say is that that in 1D you can still ask whether the solution is stable or unstable
Yes.
with respect to small perturbations, and what you say it is stable.
It's stable, exactly. That gives excitation of the solitons, the normal modes, and etc.
What happens if you have more than one king? Is this can annihilate other?
Oh yeah, okay, that's a very good question. That in 1D, because this system is so special, it is integrable. So if you have two, this system even have two soliton solutions. But they don't annihilate, but they go through each other or bouncing back, depending on the velocity. So it's a particular integrable system that they can host many solitons and they don't annihilate.
So basically, two soliton doesn't seek other. They ignore.
Yeah, so they basically they go through, and that's probably the first impression of soliton. Because soliton means that when they meet, they don't even care about each other, and they go through and become still kind of independent.
But there's a phase shift, right?
Yes, once I think when they go through, they kind of
There's a phase shift. So they do know about it.
They do know each other. Yes.
And then if I add a small perturbation of the Hamiltonian, then they will interact with each other.
Yeah, certainly. That gives if you want to know what is the perturbation, well, the normal mode of this soliton, and you add a perturbation and see how it oscillates. Or you can ask because this is a kind of mean field approach. If you ask what is the quantum fluctuation, a correction to the soliton, you can do that, and then that gives the quantum fluctuation.
And in this figure, what is unit of momentum?
The momentum is on y direction.
What was the unit of that?
Sorry?
You have 0 to 1.
Yeah, okay. So the unit k here is the 1 over the hidden length. The hidden length is basically tells the width of the soliton. So that's one can say that indeed the snake instability vanishes around the size of the soliton. That somehow tells that this instability only exists for the long wavelength excitation. Once the excitation is the length is small, then there's no snake instability anymore. Okay, yeah, please just feel free to to ask a question if I'm not clear on something.
So intuitive pictures why this transverse motion is not amplified.
Yes, I will come to your point immediately. Next slide. Yes, there is another way to understand why so. Certainly, well, the previous result that can be obtained by looking at the linear excitation and look at the eigenvalue of this excitation, and we found there's the imaginary part, and the imaginary part tells us there is the initial exponential growth of the amplitude. That's the calculation and how to understand this phenomenon. And the way to think about it is we go to the energy argument, and we can calculate the excitation energy of the soliton. This can be done by fixed chemical potential. So we have a chemical potential, and then you calculate the excitation energy about compared to the ground state of the system, and then one can say that the excitation energy are the function of velocity. And one can say it decreases as increasing propagating velocity. Now, if we expand this energy as a function of velocity, the second term, which the leading term in terms of velocity, and the coefficient must be negative because it decreases. Now, this term certainly have an interpretation of a kinetic energy of a particle. And then the coefficient naturally can be interpreted as the inertial mass of the soliton. And then the inertial mass is negative. Yes.
And this side here,
yes,
I still remember it as solution of one-dimensional equations.
Yes.
Are you extending it in some way to put this perpendicular direction inside when you're calculating this? So this is still this one-dimensional solution which was stable, as you said.
Yes. So So at the moment, this is still 1D. This calculation is 1D, and we can calculate the excitation energy and etc. etc.
And you still get this decrease.
Exactly. This is always in 1D, but from the 1D, one can say why in 2D it decays.
Okay.
It must decrease to zero. It must be negative. It must because at the velocity 1, you basically just have the ground state.
Exactly. It connects to
So
the
the
ground.
energy must become zero.
Exactly. Excitation energy becomes zero. Precisely. And of course, that's again the unit is a unit in the speed of sound. Yes.
Is distorted depend on the boundary condition. You think about the period about
No, this is not a periodic boundary because
zero.
the phase has a jump, so one cannot add a periodic boundary condition. So this is all open. This is a free space, no boundary.
So the density is always
Yes. So
diverse. But so integrate all integration over the whole.
yes, but but that's not a problem because the background is also extensive. So you basically it's infinite minus infinite to get a finite number. So that's not a problem because your background also infinite. But the side is okay. So it means that the initial mass is negative. So the initial mass is negative. So what's the initial mass mean? The initial mass means that the response to the external force. So if it's a positive, it has a positive response, like what we see every day. That's Newton's law. But if the inertial mass is negative, it means that the response is opposite. If I put something, that something accelerates towards me instead of away from me. So that's what the inertial mass being negative. So then now we come back to this scenario of that. So if we have a transverse deformation, like a robot string, and there's will be always a restoring force. Yeah. So like if we have a kind of deformation like that, we will have a restoring force on the right. But since the inertial mass is negative, it goes in the opposite direction. So that's the amplitude start to amplify. So that's why it becomes unstable, because of this negative inertial mass. Right. So that's kind of a hybridodynamic way of understanding why for the soliton, for the dark soliton, there is a snake instability. The answer is that the inertial mass is negative. And we will use this concept in a later case, and we will see that for ferrodark solitons, the inertial mass can be positive and negative. And of course, that again, that since the energy is suddenly decreases as a function of velocity, one can also see from the density profile. This is for the black line, it's for lower density, for low velocity, but this orange line for higher velocity, apparently for higher velocity, the deeper is shallower, certainly the energy of the excitation energy.
I think that your argument need two conditions. First of all, the initial mass should be negative, and you also need to show that the elastic constant is also positive. If elastic is negative and the initial mass is negative, then combine of them you can have stable.
Surely not, because if you deform the soliton, the energy of course increase.
You need to show that.
There's no, because if there's deformation, the kinetic energy, of course, increases, because the kinetic energy is the function of yeah. So if I have deformation, of course, this will give additional energy, and then of course you have oops. Okay.
Give it to
Yeah, very good question. That's certainly if you deform a soliton, the energy increases, and therefore the elastic, of course, is positive. Now, the consequence. So in dynamics, we say that indeed. So this is also a paper long time ago. They show that in 2D domain, we prepare a line dark soliton, and there will be a transverse perturbation, and you see later on the line breaks to vortex and anti-vortex pairs. So those are more stable topological defect in 2D, and yeah, so the soliton is gone. So that's what happens for soliton in 2D. And now, what I want to talk about today is so-called ferrodark solitons. I have not yet introduced what the system is, but I just want to show a picture what the ferrodark soliton looks like. So here the arrow represents the magnetization, and then the background density, the background color shows the superfluid density. So it is a magnetic superfluid that has two orders. One is characterized by the magnetization. Another is characterized by the superfluid density, the Euro superfluidity associated with a U1 symmetry. And then this soliton has has a property that regardless of the velocity, if the soliton start to propagate, the magnetization always zero. This is very different from the previous situation. Well, when the velocity is finite, the core of the soliton is no longer zero. It will fill by finite density. But for this excitation, the core always zero. All the parameter always zero at the core. All right. So this system, how to realize this soliton, and so that we have to talk about a little bit this spin 1 BEC. And normally we only have a single component because in the past the trap is magnetic. Although the atom has a magnetic structure, however, with the strong magnetic field, the lowest energy state always has a single magnetic level. Therefore, the magnetic degrees of freedom never be excited. With the progress of optical trap, all this spin degrees of freedom can really play an important role. Here we consider a condensate with the hyperfine level f is 1, and then the system has three sub-levels. I think in experiment here today we have a experimentalist doing spin 1 BEC that if this dipolar interaction can be neglected, and so in the lab people can really condensate atom in this hyperfine level equal 1. Now, then we can only consider the three sub-levels. And at a very low energy interaction, let's say S-wave interaction, and those S-wave scattering between atoms can induce spin exchange dynamics. In a sense, for the same atom, for the atom at the a different spin level, after scattering, they can stay the same spin level. But there is also a channel that the spin level can change. So that's introduce a new degrees of freedom that, for example, the two atom in a zero level, after scattering, they can go to plus and minus 1 level. So this is a very distinct from people call the two-component BEC, where there is no internal spin exchange dynamics. That's a very special property of this spinor, Bose-Einstein condensate. And in the mean field level, we can write down the Hamiltonian like this. This is the kinetic energy, and this is the density related interaction term. And this term describes the spin interaction term. And of course, those interacting coupling related to the two scattering lengths of the S-wave scattering channel. And here the Q is called the quadratic Zeeman energy. So for small magnetic field, we only have a linear Zeeman splitting. But once the magnetic field increase, so the splitting no longer linear. So there is a energy shift between the difference between plus 0 level and 0 to minus level. So this quadratic Zeeman energy play a very important role to determine the ground state of the spinor Bose gas. And without magnetic field, the system process this SO3 symmetry. While when the magnetic field is on, the system only have a SO2 symmetry. And so that's of course will manifest the ground state. And for a different atom, the spin coupling can be a negative or positive. So that's the sign of the spin coupling determines the ground state of the spinor spinor BCs. So this is a very quite short introduction. If there's anything unclear, please interrupt me.
Do you think about the quadruple interaction?
No. At the moment we don't. Yeah.
But this nematicity, in my opinion, nematicity is related to the quadruple interaction. This nematicity is really related to the soliton behavior.
You mean dipole? No. Dipole.
No, quadruple. Yeah, this is still is 1. So as a scalar type interaction is possible, right?
No, I mean,
do you know the biquadratic term?
so I'm not sure I understand the your question. The thing is that if for spin 1 condensate, if the scattering is in an S wave level, there is only 2 channels for the atom to scatter, and then if you reorganize how those scattering term, that's the Hamiltonian you can get.
You have another symmetry in the Hamiltonian is Sz equal to minus Sz.
There is of course the Z2 symmetry always there.
And then is this
But the Z2 symmetry is
only
not.
work for small magnetic field or not?
Which one for small?
I mean, is this symmetry only work for small magnetic field?
Well, if there is no magnetic field, this is SO3 symmetry. If there is a magnetic field, there is only SO2 symmetry.
SO2 plus Sz equal to minus Sz from your Hamiltonian.
Well, Z2 symmetry is included in SO2.
SO2.
It's just rotate a pi angle, right? If you rotate the pi angle, that's a Z2 symmetry.
Not sure. You rotate, so it's Sz, you rotate in the perpendicular to Z direction, but doesn't rotate in perpendicular to Z.
So this rotation is inside this is the internal rotation.
Yeah. So this is rotation is perpendicular in the Z direction.
Yes.
But the Z equal to S equal to minus Sz is perpendicular to Z rotation. You have Sz square, right? So Sz equal to minus Sc is a symmetry of the Hamiltonian.
So roughly speaking, you rotate in XY plane, but mirror reflection in XY plane is not included in this SO2. That's what is being discussed.
So this rotation SO2 rotation. It's okay. Let's yeah. So this basically it is 1. Yes. So if I take theta equal to pi, and this is
If again the
this is,
phi of your, so if you write in the Sz basic, what you do here is just change the phi of the parameter, but it doesn't make the minus Sc go to plus Sc.
well, I can so I don't find I can make also that too.
That's fine.
But
But
this is
but you
what's
will
the
not
difference
you, but
between
you will never make the Sc from +1 to -1. You can change the Sx and Sy, but you not change Sc.
yeah, I'm not changing SC.
But in your Hamiltonian, Sc go to minus Sc is the symmetry of the problem.
And so what?
I mean, so you have more symmetry than you expect.
Okay. So this if you change the basically you change the magnetic field direction, no?
No, I mean, not change the magnetic field direction. Your Hamiltonian here, if you make Sc go to minus Sc,
Yeah, because yes, that's because there is a linear term I didn't write.
good to know.
It's like a poker game.
There is a linear term I didn't write because, of course, there is a quadratic term. There is a linear Zeeman term.
I think that's one.
But I think this normalization SD is just conserved.
Yes,
SD.
and there is a concern.
Yeah. So
Yeah, and then you can't change SA because unless you change H. So I didn't write because this term does not really make a different ground state, and also mathematically you can make a gauge transformation and make this term gauge away.
Really?
I don't know whether I'm clear.
Yeah, let's please forward.
Yes, there is a linear term I didn't write. Sorry for that. And that's only because only the quadratic term matters. So I only write the quadratic term. Yes. Please, anything that I'm happy to discuss any issues on that. Okay. So for this system, we can introduce an order parameter, so-called magnetic moment. The definition is looks like this. And by the way, sorry, S here is the generator of SO3 group or spin 1 matrices. And then sometimes it's for convenience we introduce this FZ and F perp. And then the magnetic field is always on Z axis. And for anti-ferromagnetic coupling, where GS is positive, the magnetization is 0. So this is called the anti-ferromagnetic phase. And for the GS is smaller than 0, the magnetic field is not magnetic magnetization is non-zero to get the ground state, because one can say that this is basically magnetization square. If GS is negative, certainly we want to gain a finite value to minimize the energy. Right. So here we consider a particular phase. It's called the Eisen plane phase. It is in a paramagnetic phase. However, if the quadratic Zeeman in a certain range, the magnetization is finite. However, if we consider the theta magnetization is 0, therefore the magnetization only in the XY plane. So that's why it's called the Eisen plane phase, because the magnetization only in the XY plane. Now, the ground state can be written like this, and there are two angles to categorize the phase. One is the global phase, theta. Another is the phase tau. But tau is related to the SO2 rotation, basically tells that the F perp, the angle of the F perp. So we have two angles to categorize the ground state. And then clear on that. Just make sure that I didn't say something unclear. So we have two angles now. So one is the global phase, that's the Euro case, the U1 symmetry, and then there's another angle called tau. It's associated to this SO2 symmetry, where this angle controls the angle of the magnetization on the plane.
How many goldstones that you have at the end?
Goldstone.
Yeah, you break to symmetry.
Goldstone, I think. Well, as a goldstone, goldstone would be related to these two angles. This one is also related. This global phase is mass superfluid density related to mass superfluid density. If you make a twist, and then the tau related to the spin superfluid density. So there are two branches. Okay. So far we use the language of magnetization. However, in terms of a component, this tau is nothing but the phase difference between plus and 0 or minus 0 phases. So that's the phase difference between components. But this component, the phase has a nice geometric interpretation that describes the angle of the transverse magnetization. However, in terms of a wave function, that's the phase difference between those components. Hopefully, right, because I can't say in many words on that because it's very important to understand what's the difference. Okay, now since we have basically two parameters or two angles to characterize phase, to characterize the ground state, then there will be two different topological defects associated with two phases. So one is a topological defect or Z2 topological defect associated with this theta angle or the mass superscript order. People call it dark vector soliton because in each component there is a dark soliton structure, and if you look at the wave function far away from core from left hand side and equal to minus the wave function minus, okay, here we go. On the left side, equal to the minus of the wave function on the right-hand side. So that's the kink, and one can also calculate this this topological charge via the phase, the global phase. If it's a positive one, negative one, that's has soliton or anti-soliton, and zero, there's no soliton. Also no defect. And the same story, same logic. However, now if we look at the transverse magnetization, the same thing. And if there's change of sign across the core, then there will be a topological defect in this order, in this magnetic order. And of course, one can also calculate the topological charge via this phase tau. If it's an integer, zero integer, there's a topological defect. If it's no, then there's no topological defect. So that's how those defects are defined. And we are basically concentrating these defects today. Right. All right. So just give a little bit a picture on what's the topological defect looks like. And we just said the phase. However, once the phase had a jump, the density has to change accordingly. And now we are plotting here is that if you look at the magnetization, and this red and blue line shows this so-called ferrodark soliton. It has certainly a kink. But if you calculate the magnetization for this dark soliton, it does not develop a kink, but only develop a dip, but not a kink, a topological structure. And for the total density, and for the dark soliton vanishes at the core for total density. However, those ferrodark solitons only develop a dip. Therefore, that's why we always say that this topological defect is in the order parameter magnetization.
So what's the difference between type 1 and type 2?
I will come to that point later. But just give an overall what it looks like. From now, it looks like the difference only is the width.
Can you go to the previous slide?
Previous slide. Yes.
There's a definition of F perpendicular. Can you go to definition of F perpendicular?
Yes. It's just a superposition, but it seems like F vector.
Yes.
It's just for convenience when use a complex notation.
Why bother me in the following way? If density equal to 0, that means, can you go to the slide that you have? Yeah, so density is like per side sum of three terms, right?
Yes.
It's 0 at this point, but so why F still survive?
You say the dark one?
Yeah, the dark.
Yeah, the dark one, because all the component has the hyperbolic tangent. So that's why total density vanishes as before.
So if we have total density equal to 0, how
Yeah.
can you still have F?
But yeah, that's the thing. The F also vanishes, but does not develop a kink. So that's what I'm saying that for those ferroducts in the order parameter magnetization, they develop a topological kink. But for the dark type of soliton in the order parameter, they always develop a kink.
Because the definition of density is some psi 1 star
Yeah,
psi 1.
This is the total density,
Yeah.
but the F purple is different. It's not the total density, but let me go back to the previous slide. It is a combination of that.
Yeah, but if psi 1 star psi 1 plus psi 0 star psi 0 plus psi minus 1 star
Yeah,
psi 1
That
equal
gives
to
a hyperbolic tangent square. That's why it does not develop a kink. It is a square. It makes the sign flips.
And if this sum equal to 0, how can this one be non-zero?
Which one? No, it's always zero.
Okay, so
It's always zero. It's just that does not develop a kink. It's always zero.
okay.
Yes.
So spin component, but then paradox soliton is x equals 0. Does it spins are aligned vertical axis? It's just there's no magnetization at all.
You mean for paradox?
Yeah.
Yes.
Paradox,
The paradox, the order parameter is zero. Yes.
so there are finite densities,
But yes, the finite density.
and it means the spins component wise, all the spins are in x equals 0 state.
No.
And the superpositions about the constant.
No. So yes, that is always in easy plane phase.
So it means equal populations of up and down.
Yes.
That's the reason for
Yes.
there's no transverse
Yes.
magnetizations,
Yes.
but still.
Yes, still have finite density. That's absolutely fine. Right. Okay. So now we see what the soliton look like, and then luckily enough, we found that at a particular coupling constant, we have an exact solution. And by the way, it was the first experiment to realize this coupling at this around this value is actually in the audience. His lab actually firstly realized this BEC at this very large spin coupling. This is very important because for small GS, the spin dynamics is very slow. So we want to really see interesting spin dynamics. The condensate is gone. So it's for strong spin coupling condensate. This is very useful to see a very interesting spin dynamics in the lab. So okay, nevertheless, at this value, we found the exact solution of this ferrodark soliton, and the magnetization looks pretty much quite typical. It's a hyperbolic tangent. Well, I will emphasize again that for whatever velocity at the core, the magnetization is zero. While for the density, there is a dip at the core and has this hyperbolic second square, this shape. Well, the density is always non-zero at the core. Now, come to this question that there is a type 1 and a type 2. So what does that mean? It means at the moment, it only means that they have different weights. So the weights are different. And then, but we will see they are different dynamically. It's completely have opposite properties. And now there is a quantity Q here and has a little bit complicated expression. However, apparently Q square has to be positive, and this condition gives velocity bound of this soliton propagating ferroducts. And this bound is very particular in the sense that this bond is not one over the speed of sound. So previously in the scalar case, the velocity bond is bounded. Well, the velocity bond is given by the speed of sound. But this velocity bond has nothing to do with the speed of sound, in the sense that, say, in the uniform system, we can always get the Bogoliubov spectrum. In this easy plane phase, we have two gapless branch and one gapped branch. And for those gapless branches, and there are basically two type of Gaussian modes, and they involve a spin wave and a density wave. And then this slope for low k gives two velocities. And we can see our expression of this speed of the bond has nothing to do with those speed limits. Moreover, for particular large Q, and this new bond can be even larger than the let's say speed of sound of the system. And I have tried the simulation. I just put the soliton at this value, and then certainly the velocity, the propagation velocity is larger than the speed of sound. Nothing happens. There's no say generate many other degrees freedom, and it's just propagate freely. The reason is that when it propagates, the magnetization density always zero at the core. So it does not really involve any spin current go through the soliton, therefore does not really excite any interesting Bogoliubov modes. So that's why they can propagate freely, in respect to the speed the low lying excitations. Right. Okay. So so another thing, just one property I want to say that when the velocity, when the magnetization, or correct Zeeman go to zero, one can say that there's no speed. The speed limit is zero. That means that the soliton cannot propagate. That's also easy to understand, because when there's no magnetization, no magnetic field, the magnetization is conserved. So domain work cannot propagate. Otherwise, if it propagates, it will break the conservation law. And another important point is that when the velocity reaches the maximal or reach the bound, the two types of ferrodarks become identical. So this property will become important when we later go to 2D. Now, if we look at the energy plot, this is probably more clear that here is energy excitation of type 1 and type 2, and x-axis is the velocity square. And for different types now, we see the intrinsic difference. So the difference, yes, from the density or from the profile point of view, it's just the length. However, the dependence of the dependence of energy as a function of velocity is completely opposite. So for the type 1, the energy increases as a function of velocity. This is we don't see in the past. What we saw in the for the scalar case is that the energy decreases as the increasing velocity. Now the two energies smoothly connect at the maximal velocity, and therefore one can expect that at certain conditions, these two types can inter-exchange. One can go from type 1 and type 2. So what this curve can tell us again is that for type 2, the inertial mass is negative as for the scalar case. However, for type 1, the inertial mass is positive, while they become identical at the maximum velocity. So I don't know. Should I stop, hold a while, and then receive questions?
You want to finish or you want to continue?
I want to continue.
Or then-
Oh, I can. I continue. Now, indeed, if you look at we can calculate the inertial mass. Indeed, for they have a different sign, and again, consistently, when the magnetic field goes to zero, the inertial mass become infinite and become infinitely heavy, and therefore they cannot move. Now, since they have this transition between two types, the consequence of that is introduce an interesting oscillation dynamics in the presence of linear potential. Now we consider again 1D system and use hardware trapped 1D system superimposed imposed by a linear potential acting all the components equally. Now, if we prepare the soliton at the very beginning on the one end of the system and then let it go, so what happens that it shows oscillation. This is a linear potential, not in the harmonic trap. This is a linear potential, and the soliton shows oscillating behavior. So the reason is that once so initially, of course, that the soliton will accelerate because of the buoyancy force of the fluid provides, and then once the velocity reaches the maximum velocity, and the type changes, then the reaction to the external force also changes sign. Therefore, it starts to accelerate in the opposite direction, and then so on and so forth. At the end, the soliton shows oscillation behavior, and one can also look at the velocity, and indeed, once the velocity reaches the maximum, it changes types and shows this dynamical behavior. And just one point to emphasize, this is not a Bloch oscillation, because the Bloch oscillation requires underlying periodicity, and then you plug in electric field, and electron shows oscillation behavior. However, here there's no built-in periodicity. It's purely driven by nonlinearity. Okay, so here the same story, but I simply just want to show a movie, and so this is the magnetization square. And this is the component densities, and this is total density. You can see that it's just showing a smooth, very smooth oscillation dynamics.
So the period is oscillations is defined by this potential which
No.
you impose, right?
No.
It doesn't.
No, it cannot say it's the heat of the wall and coming go back. It stops before hitting the wall.
Mm-hmm.
So that periodicity depends on the interacting strength, depend on the slope of the potential, but does not depend on the boundary of this.
So it does depend on the slope of the linear potential.
Mhm.
Yes, that depends. And then, okay, now come to the point that we say, oh, there's many interesting properties, and so what from the from the soliton dynamics point of view, it might be interesting, but again, is there anything can beyond that? There is a recent very nice experiment. The purpose of experiment to show the similarization procedure of spin 1 boson gas across a quench. So this is the experiment done by a group in Heidelberg, led by Obseller. And so what they did is that they prepare 1D system, and again trapped by this kind of flat bottom potential. And then initially the system is prepared, all the ultimate is prepared at the M0 state. And then they make a quench, the quench, the correct Zeeman, and such that now the parameter is in the easy plane phase. What they want to say is that initially the magnetization is 0, and they want to say whether this magnetization can develop and then reach the easy plane phase where the phase is magnetized. That's what they do. So, and we can see that here is the plot of magnetization. Initially, it's pretty this fx and fy initially is pretty scattered because there's basically no magnetization in average. However, where time the magnetization start to concentrate on one direction. So it means that the parameter start to be in phase for different places. That's now the phase basically reach somehow the equilibrium state, which is characterized by finite magnetization. So that's what the main purpose of this experiment. And very nicely that at the equilibrium phase, they test all these elementary excitations, and that match the theoretical prediction very well. Now, there is one part it's not that well. What they observed for small q, they calculate this static structure factor. So that is this y-axis is, and this factor, this quantity can be calculated via this Bogoliubov theory, where only linear modes are considered. There's no soliton, or there's just the Bogoliubov modes. And what they found is that so for this blue line, blue band, where they have some calculation errors, that's a theoretical calculation. And then the square is an experimental data, and they say that for small q there is a significant deviation from the theoretical prediction and the experimental data. And the authors in the paper, they suspect that the ferrodarks, what we were just talking about, could be responsible for this deviation. Namely, that the system, even though it's kind of similarized, however, it's not quite completely similarized because of the long-lived nonlinear excitations is still there. So those nonlinear excitation contribute structure factor. Therefore, in this sense that the solitons, because it's so long-lived, it really slows down the similarization process like vortices, or even more. This is more spectacular that they even contribute to the equilibrium phases in the sense that even the system is reached equilibrium. There's also this nonlinear excitations involves. There's not only this linear modes contribute to the similar phase.
So basically, you're saying that in the experiment and in the theory, they calculate the quantity without considering the effect of soliton, and you say the soliton will be the reason for the difference.
Yeah. Yes. So the theory they can do is that only can contain the linear mode. That's the Bogoliubov theory. They cannot do a theory with the soliton. I don't think that people know how to do that. However, yeah, that's the data shows that there is a significant deviation. So they suspect that the ferrodarks we were talking about are responsible for this behavior. Of course, this is suspect. It's not confirmed. It's not confirmed a conclusion. Now, so why it might be indeed the case, or why it's reasonable to think at least it is possible, is that this again those topological structure of ferrodarks is kept when propagating. And moreover, that there is no spin current go through the core of the paradox, and the coupling, therefore the coupling to the low line excitation is very, very weak. Therefore, it's basically very hard for those solitons to couple with this linear modes or a thermal cloud. Therefore, or maybe if there is coupling, must be very, very small, and therefore they can be very long-lived. So that's has this potential to participate similarization and also other out of equilibrium process. Right. Okay. So far, I'm focusing on the magnetic structure of those solitons. I have never shown what the wave function looks like or in components. I want to show this because this is important for understand the instability behavior. And for type 1 soliton, the wave component wave function looks like that. This is a plus minus component, and this is a very typical, this is like a dark soliton. However, for the M0 component, you see that the interesting part is the imaginary part, the coupled to this spatial structure, the topological structure. Therefore, why when the velocity is 0, this kappa I vanishes and there's no topological structure, and therefore, so those every component looks like a dark soliton, but not quite. The combination of those components gives rise to the parameter, and this parameter always shows the topological structure of the excitation. So that's a quite interesting structure of the wave function. And for type 2, the structure basically is opposite. The plus minus 1 component has the imaginary part on this non-trivial structure. However, for 0 component, the imaginary part only acts on this is on this kind of trivial space dependence. Oh no, this topological trivial part. Okay, so but for it will become quite clear when the velocity is 0. When the velocity is 0, the structure is pretty clear. That is what is the ferrodark soliton is that the two dark solitons in plus minus component while trivial in the M0 component. And for type 2, it is opposite. That the dark soliton is resident in a 0 component. However, plus minus component it's trivial. That's when the velocity is 0. What's the structure of the ferrodarks in component wave function? Now, come to our, that's the main topic of the talk. Is already almost reached the end of the talk. But let me, okay, now what we again consider a line soliton, and we do the same thing as what we did for the scalar case. Look at the stability. Now this shows the type 1 ferrodark, and we just show that for type 1 ferrodark, the inertial mass is positive. Therefore, we don't expect any sticky instability. Indeed, we don't find any behavior like a snake. Instead, the imaginary part of the energy just does not look like any a snake instability, right? And however, this stability does exist. What this unstable corresponding unstable mode does? We call this instability as a spin twist instability. What the mode does is they generate magnetic texture in the XY plane. So they generate this so-called polar core spin vortices. Polar core means this means it's oppositely charged. We will see later what that means oppositely charged. So at the core of the vortex, a line soliton generates a chain of vortex and anti-vortex pairs. That's what this unstable mode does. And the intensity, basically only the modulation. There's nothing interesting going on. So why we identify this as a pole vortices or oppositely charged vortices? If you look at the phase of the plus minus component wave function, here the black arrow present the phase, not the magnitude anymore. This is the phase, and we can see that the plus component if there is a plus winding, and then in minus component minus winding, then in plus component there will be plus winding. It's always opposite. That's why it's called the oppositely charged spin vortices, because in terms of spin, in terms of magnetization, it shows the spin winding, but in terms of phases, they show a different opposite phase winding in plus or minus component.
So it means there's no net mass flow.
Sorry?
No net mass flow. Because
yes, no mass vortex, and the mass vortex will come later. And again, I want to show this. This is a very, see this density has a snake, but we see there's no snake. But the funny thing is that yes, in component, there are snake instabilities because again, for type 1, we have this dark soliton in plus minus component. Of course, we expect there is something, there's a kind of a snake instability in plus minus component. Yes, the unstable mode does generate kind of a snake instability. However, in plus and minus component, they have completely opposite phase. So overall, in total density, there's no snake anymore. So these two completely compensate. So that's why in overall, you don't see it's hiding in components in the opposite way. They cancel each other. And now come to this interesting part. That's for type 2. For type 2, we know the inertial mass is negative. Therefore, we expect there is a snake instability indeed. But apart from the snake instability, there's also a spin twist instability. Let me first go explain this spin twist instability. And the corresponding mode generate spin winding, but this spin winding is not in the XY plane. It is in the Z plane. So the spin winding is not in because our magnetic field is on Z axis, but this spin winding is kind of out of plane. It's not an in plane winding. And then also this winding is from not from the space winding components. This is I have never seen a spin winding which does not come from the phase winding. This is for example, at least to the best of my knowledge, I've never seen a spin winding like that. But anyway, so what most interesting part is this snake instability. And then how to see this snake? We see this the zero component density. Indeed, you see there is a kind of a snake variation and mass vortices pairs in M0 component. So that's where the mass vortices are from. That's the snake instability. This is pretty much expected because sorry. That's because for type 2, the dark soliton is in M0 component. Therefore, we expect the snake is in M0 component, and then the behavior is exactly like in the scalar case. Okay, now what happens for the dynamics? So the first row, this is to show the time evolution of the ferrodarks confined in the box potential, and then the first line is the type 1 ferrodarks. We know that the type 1 ferrodarks has a positive inertial mass. Therefore, if we have prepare a transverse perturbation, it will just like a string oscillation. It's a periodical motion because the mass is positive. It's simply just like a robot string. It behave pretty normal. Now, the second line with same deformation, but for type 2. Type 2 has a negative inertial mass. And indeed, at the earlier dynamics, we see indeed the amplitude grows. Now that's what the snake instability should do. It grows and grows. At a certain point, what we expect, it breaks. But no, it does not break. And then if we go on, this is then the time direction goes this way, and then start from here and go on. No, it does not break, but shows this quite complicated chaotic behavior. Of course, we cannot claim this is a chaos. We don't. We didn't characterize the diapolitic component or the dependence of the initial conditions. However, the motion certainly is not periodic. It's quite complicated dynamics.
So,
but it does not break.
So can one say that when it's deformed, some segment it go to type 1 and some segment is still remain type 2? Is this correct?
You got the idea. That's exactly what happens. So what happens? Let's look closely. What happens? So the same dynamics, but here now we say again type 2. We look closely. Say what is happening during the dynamics. So here, this line is the magnetization, and this is the plus component density and minus component density. Sorry, plus minus component density and zero component density. And so this is the phase, the zero component phase, which what we should really care about. That's where the snake come into. Now, we just discussed type 1 and type 2 from the profile point of view. The difference is only the width. We basically can't really see the difference, just look at the profile. The real difference is that the response to the external force. So what we do is that initially we calculate the local acceleration. That's where the blue line shows. And we can also calculate the restoring force. Of course, that's not an exact restoring force, but we calculate via their local curvature. That tells you the restoring force. And initially, we can say indeed everywhere they show opposite sign. So because we imprint the type 2 soliton, that should show the opposite sign because the inertial mass is negative. But where time locally, since this is shaded region, the inertial the force and the acceleration become the same sign here. So locally, they transform to type 2 soliton, type 1 soliton, where type 1 has the positive inertial mass. Now the ferrodark become hybridized. Instead of breaking down to vortices, it becomes hybridized ferrodarks. And in the meanwhile, in the zero component, develop mass vortices. And those mass vortices, they never become free. They're confined by those soliton lines. And so at the end, why the dynamics, later dynamics become so complicated because it's a hybridized system and also has contribution from vortices. The vortices generate flow, so everything kind of mixed up together, generate a complex motion at a later time. So that's basically what is happening in this system. So that's basically the end. So I won't really go through this summary, but I do want to emphasize that indeed there is a chance that we can see this dynamics in the lab. And thanks for your attention.
Thank you, Xiaoquan, for this interesting work. We are quite late already, but maybe we ask some questions that will be clarified right now.
How stable about your scenarios against these. I think there are scenarios about this specific point where your state interaction is about half this thing dependent on it. So I wonder how it's proposed against experimental. For example, the mutant cases they are away from this point.
Yes. That's a very good question. So the solution of this type of soliton exists in the whole independently, and we have tested. But although away from that point, we don't have any formula, but numerically we see the existence of that. And also, what I show all those behaviors does not only hold at the exact solver point, but also away from it. The property question.
Okay, more questions? Well, if that's not the case, let me just say also that Xiaoquan is staying with us until I think roughly the end of next week. So there's still a lot of chances to interact. So please do that. And with that, I think we have some food, I hope, outside. So thank you very much, Xiaoquan, and thank you to everyone. Thank you.